Okay, so in this video, I'm going to show you an example of one of these acid-base titrations where we're going to calculate the pH of the solution. Okay, so let me bring this problem up. There we go. Okay, so this is calculating the pH of a weak acid titrated with a strong base. So an analytical chemist is titrating 219.9 milliliters of a 0.4400 molar solution of hydrozoic acid, HN3. Be careful, that's not ammonia. It looks like ammonia. NH3 is ammonia. This is HN3. With a 0.5500 molar solution of sodium hydroxide, NaOH. The pKa of hydrozoic acid is 4.72, and you want to calculate the pH of the acid solution after the chemist has added 186.9 milliliters of the sodium hydroxide solution to it. Note for advanced students, you may assume the final volume equals the initial volume of a solution plus the volume of the NaOH solution, and round your answer to 2 decimal places, right? So we're going to calculate a pH here, and what's important about this one is that we have a weak acid, right? How do I know that hydrozoic acid is a weak acid? There's a couple of different ways. One is it's not one of the common strong acids. There's 7 common strong acids. This is not one of them, 7 or 8. But the other way is that it's given a pKa. The pKa is 4.72. And when an acid is given a pKa, that typically means that it's a weak acid. So we have a couple ways of telling that. Now, it's reacting with sodium hydroxide. Sodium hydroxide, we know that's a strong base. So this is a weak acid with a strong base, okay? Now, your approach to the problem, in a sense, is the same no matter what, but there are some very fine details of how the pH will work out depending on the numbers. This is one of those types of problems where it depends on what the numbers are, can change the result dramatically. And it actually can change how you calculate your final answer. So you have to really pay attention to the numbers. So we have 219.9 milliliters of 0.44 molar HN3 with a pKa of 4.72. And we have 186.9 milliliters of 0.5500 molar NaOH. You want to write those numbers down and then on a piece of paper, go through the calculations. So let's take a look. I'm going to go ahead and bring up the screen and we'll approach it. The first step is to calculate, I'm sorry, not to calculate. The first step is to write the chemical equation for the reaction. So I'm going to write it this way. I'm going to say we have an acid. We know it's an acid. It's not a very common acid. And then that is going to react with a base, NaOH. So, you know, we can switch partners, but essentially what happens is the H plus in the acid reacts with the OH minus in the hydroxide, and that gives you water. And then you're going to get your salt as well. So you have the metal is sodium, that's your cation, and then you have the azide ion, N3. Now, sodium salts are aqueous, they dissolve in water. Water is a liquid, so these are all aqueous with the exception of water. I'm going to write that out. Don't have to worry about the stoichiometry here. There's not like we're going to have 2 of them or 3 of them or anything like that. We're just going to have a 1-to-1 ratio. Most of the problems that we look at in this course are 1-to-1 ratio for the acids and the bases. Okay, so now the next step, what I'm going to do is I'm going to write down the initial number. So I for initial, the initial number of millimoles. So I'm going to do a little calculation here of millimoles down here. MMOL. And why am I doing millimoles? The reason I'm doing millimoles is that very often when you do these problems, the volumes are given in milliliters. And so instead of getting rid of the milli and converting it to liters, it's actually more convenient just to leave it in milliliters and then get moles out of the calculation. Okay, so let's do the HN3 first. It's 219.9 milliliters, that's your volume. And then the molarity is 0.4400. And I'm going to go ahead and write it out explicitly. Molarity is moles over liters, right? And what you're going to get out of this is millimoles because the liters will cancel. So you get the number of millimoles. Okay, so let me pull up my calculator here and we'll go through this. So it's 219.9 times 0.44. And you get 96. One of the things you get used to in these calculations, you're not going to get nice round numbers on Alex. You're going to get some really like lots of decimal place numbers, right? So 96.756. So that's the number of millimoles of HN3. Okay, that's the initial. So I'm going to write this down, 96.756, and that's millimoles. Okay. Now let's do the same thing for the NaOH, millimoles of NaOH. The NaOH is 186.9 milliliters, so 186.9 milliliters. And the concentration is 0.5500. Again, molarity is moles per liter. Okay, so 186.9 times 0.55, and you get 102.795 millimoles of sodium hydroxide. Okay, so that looks pretty good. So I'm going to write that down over here, 102.795 millimoles. Okay. Now, let's do the change. Now, I know that when we did equilibrium calculations, we often referred to this as initial change equilibrium. Here, it's really going to be initial change in an ending, the final point, okay? Because we're not really talking about an equilibrium calculation here. We have a strong base reacting, so it's going to go to completion. This reaction will occur until one of them runs out. Which one do you think is going to run out in this reaction? Which of those two reactants do you think will disappear before the other one disappears, right? React completely. It would be the smaller number, right? The smaller number is the limiting reactant. So the HN3 has around 97 millimoles. The NaOH has around 103. So there's more of the sodium hydroxide. So here's what happens. They react with each other until the limiting reactant runs out, which is the HN3. So they both go down by the same amount. The limiting reactant. You can't lose more than you have, right? You can't spend more money than you have. You can't lose more chemicals than you have. So if you only have 96.756 millimoles of HN3, the amount of HN3 that can react is that amount, and the amount of NaOH that can react is that amount. So what happens then is you get products out of that. One of the products you're going to get is NaN3. Okay, right? That's going to go up by some amount, right? Why does it go up? Because it's a product. When you react to reactants, you get products. So it's going to go up by that same amount. Okay. So now, once you're at your end point, E for ending in this case, you're not going to have any HN3 left over. That's going to be 0, right? Because you reacted it all. But you will have some NaOH left over. Okay, now how much NaOH are we going to have? 102.795 minus 96.756. Again, you really got to be very careful. You're entering in a lot of numbers. So you're going to end up with 6.039 millimoles of NaOH. And then you're going to have 96.756 millimoles here. Now, I'm going to circle these two numbers here because both of those numbers have to be considered. As I said at the beginning of the problem, it depends, the details of this depend on what's in the final solution and how much of it is in the final solution. You have to be able to evaluate the products. So in a sense, even though NaOH was a reactant, it's there at the end. So it's kind of like the product of the whole process is still there. But there's no more HN3. So what do we have here? We have a strong base, right? Sodium hydroxide is a strong base, and we have a weak base. Now, how do I know this is a weak base? That's not obvious, right? It may not be obvious. This is from chapter 16. Remember what we said is that if you take a weak acid and you take off an H+, you're gonna have the weak base. It's called the conjugate base of the weak acid. So when we run this reaction, we actually end up with some weak base in the product. And so we have a strong base and a weak base. So typically the way we deal with that is that if we have a strong base and we have a weak base, essentially the strong base will dominate the pH. And the weak base is a negligible in terms of the pH, negligible effect on pH. Okay. Now that is not always the case. And to be honest with you, these numbers are kind of extreme, 96 millimoles as opposed to 6 millimoles. But even in this case, the sodium hydroxide will most likely dominate the pH. So how do we calculate the pH of a strong base? Well, the way we would do that is we would first find the concentration of the base, hydroxide, right? So that would be the number of millimoles of the hydroxide divided by the milliliters of the solution, right? Well, how many millimoles of sodium hydroxide do we have? 6.039. Right? Now, what about the volume of the solution? Remember at the beginning, it said for advanced students, you can just add the two volumes together. In fact, when you add volumes together of liquids that have solutes in them, the volumes actually are not necessarily additive. 25 plus 24 is not necessarily equal 49. It might be 49.1 or 48.9, but they're saying forget all that. We need to worry about it, just add the two together. So what we do is we add the two volumes together. Those are two volumes. The whole solution will now be a mixture, right? So if we add those two volumes together, 219.9 plus 186.9, you get 406.8. Okay. Now what I'm going to do is I'm going to calculate the concentration. So I'm going to take 6.039 and I'm going to divide that by 406.8. And I'm going to get a concentration of 0.0148. And what's the units? Millis cancel, moles divided by liters, right? There's your molarity of the solution. Isn't that interesting? Okay. So now we've got the concentration. So let's calculate POH. See how all this stuff from chapter 16 keeps coming back? Minus the log of the concentration of hydroxide. So minus the log of 0.0148. So my calculator here, 0.0148, oops, minus the log of 0.0148, and you get 1.83. It's 1.8297, but I'm just going to round it to 2 digits, 1.83. And then your pH is 14 minus that. I hope you remember that from chapter 16. So that's what, 12.17. And there you go. Now, in fact, this might add a little bit of hydroxide to it. So it might lower it to 12.15 or 12.13. But typically we can ignore that contribution. And we would have a pH of around 12.2, 12.17. Okay. Now, I want to make a point about this particular problem, and that is because we had more hydroxide than we had acid, HN3, that meant that we had an excess amount of hydroxide. So that meant the solution was basic. And so we calculated the pH based on that. That is not always the case. You could have numbers such that you are left with a little bit of HN3 left over, and the sodium hydroxide is the limiting reactant. If that happens, then we're going to have to use a different approach. So you have to be very careful in terms of how you evaluate these problems. If you were to have some of the weak acid left over, you would have a weak acid and you would have the conjugate base, NaN3, right? So what is that? What do we say about that? When you have a weak acid and a conjugate base, that's called a buffer, right? And how do we calculate the pH of a buffer? The Henderson-Hasselbach equation. pH is pKa plus the log of the concentration of the base over the acid, right? So be aware that if you're left with some base, if you're left with some acid, the weak acid, and you're left with the conjugate base, you're going to have conjugate base for sure, then you can use the buffer equation.